Hello everyone, this is Professor He. Nice to see you again. The topic of this task is about the Otto cycle and its optimization. The Otto cycle is the ideal cycle for spark ignition reciprocating engines. It is named after Otto, who built a successful four-stroke engine in 1876 in Germany, using the cycle proposed by Frenchmen in 1862. In most spark ignition engines, the piston executes 4 complete strokes within the cylinder, and the crankshaft completes 2 revolutions for each thermodynamic cycle. These engines are called four-stroke internal combustion engines. The Otto cycle is the particular case of dual cycle when the cutoff ratio is equal to 1. Therefore, the Otto cycle can be analyzed following the procedure for dual cycle with cutoff ratio of unity. This means the constant pressure heat addition disappeared and the state 3 merges with the state A. From equation 10.7, the thermal efficiency with the setting of cutoff ratio of unity is. It's found that the efficiency is monotonically increased with the compression ratio, and it has nothing to do with temperatures of T1 and T3. Again, when all the obstacles are overcome, the thermal efficiency of the Otto cycle can be very close to the limitation of Carnot efficiency, and the net work output per cycle will be quite close to 0. Therefore, there should be a compromise between the thermal efficiency and the net work output. With net work output per cycle, a larger mass flow rate is needed to maintain the same expected power output, which may not be economical, especially for the vehicles. With the change of the compression ratio, there must exist maximum error between T1 and T3. The compression ratio in this case is called the optimal compression ratio. Firstly, let's talk about the optimal compression ratio. Following the process for the analysis of dual cycle, we can obtain optimal operation properties. The cyclic specific network is the temperatures can be determined based on state 1 and the process we have. For the isentropic compression process, state 1 to state 2, we have this relation. For the isochloric heat addition process, state 2 to state 3, we have this relation. For the isentropic expansion process, state 3 to state 4, we have this relation. With the determined T1 and T3, only T2 varies with the compression ratio. Then we have derivatives. This implies the cyclic specific network W net has a maximum value until T2, and then the compression ratio, which could be found with the setting of 0 first-order derivative. And The solution then is, from these results, we have important conclusions. When the end temperature of compression is exactly equal to the end temperature of expansion, the cyclic specific network with isochloric heat addition and isochloric heat rejection is the maximum. At this time, the optimal compression ratio is. This is equation 1018. Secondly, with the optimal compression ratio, equation 1018, the dimensionless maximum cyclic specific network can be expressed as. This is equation 1019. Similarly, the optimum thermal efficiency can be expressed as. This is equation 1020. The thermal efficiency is found determined by the compression ratio operating between T1 and T3, while the optimum depends only on the ratio of T3 and T1. With the optimum properties, the optimum mean effective pressure is determined as. With the cold air standard assumptions, the MEP with the optimal compression ratio of Otto cycle is also determined by the temperature ratio of T3 and T1. I have two questions here. Can you try to find the compression ratio for the maximum MEP? Is it the same as that for the maximum cyclic specific network? Okay, that's all for this task. Thank you very much and see you next time.